Okay, so this is the introduction to chapter 12 called the chi-squared, a Greek letter shaped like an X, but it's really a chi-squared. And I gave this lecture Wednesday, but I'm repeating it now to have it videotaped as really an introduction. We already have a videotape of the example that comes out of this formula, but now I'd like to show you where the formula comes from. To go back to material that we've had before, let's say you want to compare the grades of two groups of people in a class or a population, and you take a sample of, let's say, females versus males, and you get the female grades on a test, let's say, were 92, 87, 61, 48, 36, and 85. And the male group tests were 74, 86, 39, 91. So we have 1, 2, 3, 4, 5, 6, 7, 6 females, 4 males, and these are the grades. How would you go ahead? How would you compare them? Well, I'm asking rhetorically because Stat 1 class is here now. But the answer is, that's in fact what we're going to learn about. Maybe this is not a bad introduction to chapter 9, which we're about to start for the Stat 1 class. You would basically get the average of this group and the average of that group and compare them according to the formula of chapter 10, which says H0 mu1 equals mu2 versus H1 mu1 not equal to mu2. And again, for those of you sitting here from Stat 1, this is what we're going to learn about over the next couple of weeks. This is like towards the end of it already. That's one approach to use chapter 10. But we can also use chapter 11, which is this is the t-test from chapter 10. But you can also use the f-test, the ANOVA from chapter 11, where you basically, that works mu1 equal mu2 equal mu3 equal mu4. But the fact that we only have two averages or two groups still works. So you have a choice. But now I'm going to change. So to answer the question from chapter 12, you can use chapter 10 or 11. But that's if you're given the data like this. But what if you're given the data not as numbers, but just pass or fail? This guy passed, this guy passed, this guy passed barely, this guy failed, this guy failed, this guy passed. This lady passed, failed, passed. So how would you can't calculate an average of these PPPs and FFFs. So what you can do, and this is after some discussion, people mentioned you get the percentages. There were 4 out of 6 people passing. There were 3 out of 4 people passing. So the pass rate is 75% for the males. And for the females, I think it's 67%. 4 out of 6 is 2/3 is 67%. So the question is, not so much are the averages the same. If you're going to express this in terms of fractions or percentages, you might want to say, is the percentages the same from the first group and the second group versus the alternative that the percentages are not the same? Well, it turns out the book shows you a formula, in fact called the Z formula, or Z version of the formula related to the Z table, to solve this kind of problem. But later on in the chapter, the book has a situation where you don't have just 2 rows and, so how can you express this number in a way that will solve the problem? Let's back up a second. Well, you can organize this data in the following way, as we actually did in chapter 4 or 5 in Stat 1. You can have 2 variables, call this the sex variable, of which there are 2 types, males and females. You can have the pass-fail variable, of which there are 2 values, pass and fail. I'm going to say yes and no because I don't want to avoid the confusion of the F for female. So yes for passing and no for not passing. Maybe pass with a question mark might be a better expression of this variable name. Yes or no. And it turns out there were how many males? There were 6 males, of whom 4 of them passed, 2 failed. The females, there were 4 females, 3 of whom passed and 1 failed, which means there were 7 people who passed in general. There were 3 people who failed in general, irrespective of the sex, and 10 people who were sampled in general. So how would you solve this problem? Basically answer the question, are the percentage of males passing equal to percentage of females? Recognizing that this was another branch of mathematics, that if it turns out to be even off by a little bit, you would say that the numbers are different, and 67 is not the same as 75. Is the same, but we want to know. But in statistics, and again, the Stat 1 class who's sitting here doesn't know about the fact that in fact, it's going to be the main part of today's lecture is to emphasize to you and get you to understand that in statistics you have to have a certain amount of variability. You don't expect perfection. It's not like geometry. You allow a certain amount of variability. So the question is, are these two numbers close enough together for us to say this hypothesis is basically true, or are they very far apart? And that's so the formula for answering that question is based to a large extent on a formula we had in Stat 1 in Chapter 4, which was the probability of two events happening, event A and event B, is equal to the probability of A times the probability of B. In other words, they call the multiplication rule, if you recall that terminology. Multiplication rule. But that rule can only be used, again, we're trying to figure out the joint probability is equal, you can decompose it into two separate little probabilities, and that rule only works if A and B are truly independent. And I just realized I left something out in terms of this derivation, or in terms of this explanation. What I'm trying to say now, I left out an important step, so let's go back up. So the book I started telling you has a formula for this type of a problem and another formula for the case of independence, but it turns out both those parts of Chapter 12 could be solved by the same exact formula, so I'm going to show you the slightly more complicated formula that will solve all the problems as opposed to teaching you two separate formulas. So the question is, when you have, let's say, 3 rows and 3 columns, you can't talk about P1 equals P2, because now you have, if you have 3 rows here, you can't say passing, let's say there are 3 columns. So you can't say passing percentage, like here, 4 out of 6 males pass. What if you have pass, fail, and, I don't know, drop the class? So you can't figure out a ratio of, of one to the other, because there are 3 of them. So what I'm trying to say is the following, that you can express the same exact question, are males and females have the same passing rate, by asking the following question. Is there a relationship between one variable and the other variable? In other words, does knowing something about somebody's sex status help you predict if they're going to pass or fail? If it turns out there is a relationship, and by the way, I gave the same lecture when we were doing Chapter 4, if it sounds familiar to you, because this is simply an outgrowth of Chapter 4. So if it turns out there's a relationship between the two variables, the only way that's possible is if the males are doing differently than the females. Or conversely, if the males, let's say, for example, 4 out of 6 and let's say 8 out of 12, the percentage is exactly the same, both 67% and 67%. If the ratios from 4 to 6 and this to this are exactly the same, then nobody could claim that somebody's sex seems to influence the chance of passing. Of course, males pass at a certain rate and females pass at the exact same rate. So the sex seems to be irrelevant. So the question about, is there a difference between males and females, which is what we're trying to answer here. Is there a difference in terms of their passing or failing in this particular case? That can be answered by putting down the other hypothesis, which really applies to all the examples of the chapter, that the two variables of classification are independent. Independent. Okay. Independent, meaning that this is one variable of classification, because again, along the rows of the table, we're trying to classify, in this case, it's just 2 possibilities, male or female, but we could classify somebody according to race, black, white, Asian, for example. And you have, but it's still the variables of classification is according to somebody's race, or in this case, according to somebody's sex. And the other variable is also just classifying pass, fail, or yes, no, and maybe, and just some classification. What kind of car do you drive? A Honda, GM, Ford. You're just classifying people. So we call them the 2 variables of classification, and there are 2 of them because there's going to be one along the rows and one along the column. Always going to be 2 of them are independent. The H1 is no, that there is a relationship between them. The 2 variables of classification are not independent or dependent, if you want to call it by a word, dependent. So how are you going to decide? Now, again, if it turns out the proportions are exactly the same, then it's easy. But what if they're, like in this case, it's 67 and 75? They're pretty close. So probably it turns out that somebody's sex doesn't really greatly influence their choice of affect their pass or fail.